Thanks for having me up here. So today I'll present on our work on accelerating SPECFEM++ with explicit SIMD, that is Kokkos SIMD, and using custom layouts. So before I go into that, let me give a brief introduction into SPECFEM++ itself. So SPECFEM++ is a spectral element code for simulating wave propagation through heterogeneous media. Essentially, we use it for simulating seismic simulations, but some people use it for other things. The goal is to use adjoint simulations to image what the Earth looks like inside using comparing realistic seismograms to synthetic seismograms. We have a diverse user base, and the code is split up across 3 repositories, and we run across machines in US as well as Europe. So essentially, SPECFEM has been developed since '99, and it's been developed as a set of 3 packages, that is 2D, 3D, and 3D globe. It's a Fortran package developed since '99, over 150 lines of code, supports NVIDIA and AMD architectures using CUDA and HIP, and threads using OpenMP. The SPECFEM++ effort itself is driven by to provide a single interface to run 2D, 3D, and global simulations. As with the key focus of modularity, that is able to write dimensionally independent code. It should be easy to implement new physics and easy to integrate novel methods. On top of that, we want to develop the code with a portability in mind that is able to run in high performance across multiple architectures. And as most people over here, we are using Kokkos and C++. So to recap, it's a complete port of the Fortran package into a C++ package. So the Fortran package still remains active while we develop this. Today I'll talk about a practical use case in our simulations where we utilize SIMD to speed up our simulations. I'll start with the baseline algorithm, dive into the SIMD algorithm, then optimize cache layouts, cache usage through custom layouts, and few key takeaways and wish lists that I have got for the Kokkos team. So let's start with the baseline algorithm. So at the end of the day, since it's a wave simulation code, at the end of the day is what we are interested in is computing gradients. So the top equation that you see there. In spectral element formulation, it looks something like that. Let's not dive deep into that. But if I were to look at the code itself, how I would write this as code, you have F, which is the field. Sorry. Yeah. F here, which is the field, which is a 3-dimensional view. It's in our case right now, it's layout right. We have the outermost for loop over the spectral elements. Then we use k as a caching variable. So in Kokkos terminology, this would be a scratch space where we load the field for that element, for a particular element in k. Then we have the inner 2 for loops over all the GLL points. And then finally, the innermost for loop, which is the summation that you see above. So if we compare the performance of this baseline algorithm, on the x-axis, we have the total number of spectral element. On the y-axis is the simulation time. The circular dots is the Fortran performance. That's what I would consider what we want to beat. And the triangular is the SPECFEM++, which we are using Kokkos. So right now you can see takes about twice as long for the C++ version compared to the Fortran version. If I look at this innermost loop and visualize it, at the end of the day, what we are doing is we are doing a dot product between, the first line is doing a dot product between the first row of k into a row of L prime and storing it into a temp. And then the second line does a dot product between the column of k and the row of L prime and stores into temp1. The problem here with vectorization is that we have uneven access patterns. So either with layout right, either we can get a continuous access pattern in k for the row or the column. And then the second thing is we are reducing the rows into a single value, which kind of serializes the code. The main thing that we want to notice, so this essentially is not very attuned to SIMD data types. The way I want to think of SIMD data types is they are data parallel types, so we shouldn't think them as ways to input vectorized instructions in your code. Ideally, you should be able to replace SIMD intrinsic types with just SIMD types, which essentially ensures that you have the same operations on different lanes. So let's look at a SIMD version of this algorithm. So there I introduce another view called the SIMD view, where I create a Kokkos view of SIMD types, so essentially the SIMD length is built into it. Now my K vector, or the K matrix, is of SIMD view, and rather than loading a single spectral element, I load a chunk of spectral elements, or it's from iSpec to iSpec plus chunk. And then my temps are again SIMD types. To visualize this, it looks something like this. So now every loop, the outermost loop, rather than working on a single spectral element, it works on a chunk of spectral elements. And then the inner loop progresses in time, something like this. Now, with that, the other thing I wanted you to note is now my F, the field, is stored as layout left. That is, the spectral element index is contiguous in memory. With that layout, I can ensure that my both row accesses as well as the column accesses are contiguous in memory, which essentially enables us to use SIMD. So with that, so the newer algorithm has a performance that's on par with the Fortran code now. However, we could still do better. I still have about 8 minutes to present. So now, we are right now on par with the Fortran code. So let's look at where the performance is being spent. So what I want, this is the flame graph of our total application. The boxed part is the computation of the gradient. And we see that about 70% of that time is loading the memory from the cache, or from the views. So we can optimize this better. And this is essentially loading F into K. Now, if I look at how my data is laid out, on the leftmost side, I have the finite element mesh. Let's consider we have a completely regular mesh, an easy looking mesh. And let's take the two elements right next to each other, n and n plus 1. Now, I said my layout is layout left, so the spectral element indexing is continuous. So essentially, when I store this in memory, 0, 0 of n gets stored first, then 0, 0 of n plus 1 gets stored next. Then there's a stride of n spec, the total number of spectral elements, and then 1, 1 of n gets stored, 1, 0 of n gets stored, and then 1, 0 of n plus 1 gets stored. Now, when I load this into K, I want to load, let's say the SIMD length is 4, I want to load 4 contiguous elements, that's corresponding to 0, 0 for every element. Then there is a strided access of n spec elements, after which I load the 1, 0 of the spectral elements in question. It would be nice if my access pattern looked something like this. That is, if I could load the first 0, 0 elements, quadrature points of all the elements, the chunk elements, and the 1, 1 lays right next to it. So that's the optimization that we did next. So the way we store this data now is in a tiled format, where the tile size, or the chunk size, is equal to the SIMD length for the architecture. And then every tile is stored contiguously in memory, and within the tile, we have layout left. So now our access pattern looks something that's more nicer. And to do this, we use Kokkos views to store the data and std md to access the data. So with that, the performance improved a bit. Now, this is a log-log scale, so you can't see the full improvement. You can't visualize easily quantify the full improvement, but we do see that the improvement, there's an improvement from the SIMD version to a cache-optimized version. Lastly, I have just another way of plotting that same improvement. So we started with a code that is about 85% slower than the Fortran version, and now which is about 25% faster than the Fortran version. So it's about a 2.5x improvement. This was on CPUs. On GPUs, we see lesser of an improvement because we are still bound by how fast we can load the data from memory and the computation, and that takes about still 30 to 40% of the time because that's our warp stalls there. And there is still room for improvement there. So lastly, I want to talk a few key takeaways. So if you're implementing SIMD types, you should think about them as data parallel types and not as not as a lieu for using it as a vector instruction in your code. So you need data parallel algorithm. If you can optimize data layout based on your data usage pattern, many times you might not be able to do that, especially if you're developing a library. And finally, the other thing I found out was index computation can be sometimes an unnecessary expense. So for example, in our code, we have a code snippet that looks like this. That is, we want to access properties for a particular JLL point. These properties are stored in Kokkos views, and all those views have a same layout. So every time I say row, ispec, iz, ix, that index computation needs to be done. And that can take a lot of resources. With mapping, we can get a linear index from the mapping and then access the views through that linear index. And this is essentially how you would do it in CUDA code, right? You get the thread ID x and then access your linear data with thread ID x. The last thing I had was a wish list. So right now we have a way, I'm using Kokkos views as my data storage and std span as my mapping. So ability to customize view layout. I know that Damien spoke about it. It's coming in 4.7, so that'd be awesome. And the other thing is the 40% of our time, especially on GPUs, is spent in loops that look something like this. It's a range loop that goes over all the quadrature points. And then there's very little work to do within each range loop. What I see is that there's very little instruction level parallelism for those loops. So it would be nice if there were loop unrolling semantics that I could directly use so that I don't have to launch n globe number of range. Yeah. With that, questions?
Okay, let's thank the speaker again. Do we have questions? Questions? Yes.
Okay, I have to admit I'm always a little skeptical about these comparisons against, compared to some old Fortran code. Mm-hmm. So I'm curious, it looks to me like basically the Fortran code was getting the SIMD optimization for free.
Yeah.
And my question then is, if you do the same cache optimization in Fortran, does the C++ still outperform the Fortran, or do we have to, is there something going on, some overhead in Kokkos that is getting in the way?
The short answer is I do not know, because essentially I would have to look at the assembly code to figure that out. What I will say is that there is the cache optimization in Fortran as well, where we store it into a dummy variable k. But in this case, I'm using chunk of elements, right? There they don't use chunk of elements. So I don't see an easy way for them to get Fortran, like for the compiler to see that vectorization easily. So
right, what I'm saying is if you implement the same thing in C++
I would assume, yeah, I would assume that it goes faster. The Fortran version would go faster, but that's a test that we haven't done. Yeah.
Okay.
And again, the goal is to get par performance with the Fortran code so that people start using the C++, because if it takes twice as long to run your simulations, no one's going to use it.
Okay. Do we have more questions? If not, let's thank the speaker again. And